Okay, so what we're going to do right now is something called enthalpy. Enthalpy is probably one of the harder topics I teach in this particular chapter, only because it's so easily confused with the word heat. It's not the same thing as heat. Heat is not a state function. The amount you have, if you burn more natural gas, you're going to get more heat. Enthalpy is abbreviated as H, and it is a state function because it doesn't depend just on the amount of heat that's produced. It is the amount of heat, energy, used or released in a chemical reaction, but here's the big thing, per mole of reaction. That makes the big difference. Okay, so there's all kinds of enthalpies. This one is probably the kind of generic failsafe. However, it means enthalpy of reaction. Enthalpy of vaporization is another version of that. It's kind of like a sub of it. It's for boiling, okay? Or enthalpy of solution, that's when you dissolve a solid in water. It produces heat or it takes in heat. And enthalpy of combustion, when you burn something. They're all kinds of this, but they're specific to a particular kind of reaction. But they're all done mathematically the same. And what makes delta H a state function is the fact that it's calculated on a per mole basis. So the units are kilojoules, which is a heat term, over moles of reaction. And let me go back to my analogy. So natural gas. So let's say I burn a little bit of natural gas in my furnace. I'm going to get a little bit of heat. Okay? When I take the amount of heat and I divide by how much natural gas I use, that gives me the enthalpy. But let's say I decide it's really cold outside and I'm going to burn lots of natural gas. Those moles go right up. But so does my heat. So that when I divide it out, it's still the same number. That's what makes it a state function. The fact that it's independent of how you get there. I can use a little bit of natural gas and I get a little bit of heat. When I divide it out, it's the same number as if I used a lot of natural gas and I got a lot of heat. That's what makes it a state function. When you use enthalpy, it's usually used one of two ways. Either you're calculating the enthalpy or you're calculating the amount of heat. This is delta H, that's heat. And it's usually from a chemical reaction or a process. To calculate the heat from a temperature change, this is what you're going to use. These usually are in joules. This is usually in kilojoules because chemical reactions produce a whole lot more heat than a temperature change. So to calculate the heat from a chemical reaction, you're going to use stoichiometry. And you're going to use an enthalpy term as one of your conversions, and I'll show you how that's done. But if enthalpy is given as part of the problem, it's given in kilojoules per mole of reaction. And this takes a little while to get used to, but you'll see how it works. It's not that bad. What you're going to do is you convert whatever your starting amount of whatever it is into moles, just like every other stoichiometry, and you're going to use stoichiometry to convert to heat, which will be joules or kilojoules. So this is the equation we're going to do. You're going to take your moles of reactant or whatever it is they give you. So if they give you grams, you're going to convert to moles. If they give you liters of a gas at STP, you're going to convert to moles. If they give you a solution, everything converts to moles first. You're going to do coefficient of the reactant, and then you're going to use this term that we're going to refer to a lot as 1 mole of reaction. So within that reaction, it's always going to be 1 mole of reaction. You might have different coefficients, but it's always 1 mole of reaction. Then you're going to multiply by this right here, and that is delta H. Kilojoules, which is enthalpy, over 1 mole of reaction, because that's what it's given as, kilojoules per mole of reaction, and that will give you the total amount of heat. This is actually delta H. I should write it that way. Okay, so sample problem. I've got a balanced equation. They're burning something here called propene. Calculate the heat release, and that means that we want Q. So when you set this up, you want to pay attention to what you're trying to solve for and what you're given. And you want to also remember kind of our conventions. So when I set this up, I do 8.9 grams C3H6. And the first thing you do is change from grams into moles, which is 42. And then you look at your balanced equation. This is C3H6 I'm starting with, so it goes on the bottom. And if I was doing normal stoichiometry, I'd turn it in carbon dioxide or water or something. But I'm going to turn it into 1 mole of that reaction. And in that 1 mole of reaction, there are 2 of those guys. And then I'm going to use this number, the delta H, to convert from 1 mole of reaction into kilojoules. So it's done like every other stoichiometry you guys are used to. It just throws in a little bit different term. And right there, remember, negative means that it is exothermic. Heat is released. That's all it means. Doesn't mean the energy is negative. All right, so if I was to do this one, same idea. I'm going to start with my 81.3 grams of oxygen. First thing I do is change into moles of oxygen. 2, not ox. And then I'm going to put oxygen on the bottom, and I'm going to convert it into 1 mole of the reaction. And that is a coefficient of 9. And then 1 mole of the reaction is negative 2058 kilojoules. And you get negative 580 kilojoules. Okay, so it's not that hard. It's just changing it a little bit in terms of calculating energy. So for this one, we're going to do it, let's go back here. Nope, not back there. This one. We're going to do it a little bit different. We're going to start with heat, and we're going to convert into grams. So it's kind of the exact reverse stoichiometry. Start with 515 kilojoules, and I'm going to notice that it says release, so I'm going to stick that negative in there, because otherwise we get negative mass, and there's no such thing. So I'm going to put kilojoules on the bottom. Here's my delta H that converts between kilojoules and 1 mole of reaction. And then 1 mole of reaction produces 2 C3H6s, and 1 mole of C3H6 is 42 grams. So you end up with 21 grams. So if I didn't stick that negative in there, I would end up with negative 21. You can't have negative mass. That doesn't make any sense. Now, I'm okay with you recognizing that this is exothermic because it says release, and this is exothermic, and just kind of taking those out of the picture. Got to keep the 2 though. And that's okay. But you have to recognize that. Otherwise, if you get a negative mass, that's telling me you're not thinking very hard. Okay, so this one, now we have numbers for both reactants, and we want to figure out how much heat is released. That means it is a limiting reactant problem. So when I set this up, I'm going to treat it exactly like any other limiting reactant. I'm going to change from grams to moles. And then I'm going to change from C3H6. And here's the thing. Because I want to minimize the amount of writing I'm doing and the amount of stoichiometry I'm going to do, I'm going to change it into moles of reaction, just like we did before. And I'm going to change it from 1 mole of reaction into how much enthalpy it's going to get. And I'm going to calculate how much heat that reaction would produce, negative 1838 kilojoules. Okay, I'm going to do the same thing with the oxygen. 185 grams of oxygen, 32. There are 9 oxygens in 1 mole of reaction. 1 mole of reaction, negative 2058 kilojoules. And I get negative 1321 kilojoules. So now I have to decide which one of my reactants is the limiting reactant. And in the past, I've always said pick the smaller number because that tells you which one's limiting. It produces less. However, with the negatives here, I just want to remind you that that means it's exothermic. Energy is not negative. What you are looking for in a heat problem is the smallest magnitude, not the smallest numerical number. That means this is how much is produced because my limiting reactant is oxygen. Okay? You're not looking for the smallest number on a number line. What you're looking for is the smallest magnitude because whichever one of them produces less heat is going to be limiting. Okay? Let's put it a different way. Here's a different kind of problem. Okay, you always need to start by finding the moles of whatever it is you're dealing with. So if I have a solution, remember liters times molarity gives you moles. If it's a solution, I'm going to start with those liters and I'm going to multiply by the molarity. But I'm going to continue. Once I get into moles, all I have to do is change from my whatever I started with into 1 mole of reaction. And then 1 mole of reaction is negative 56 kilojoules. And all I have to do is multiply, so it's negative 15 kilojoules. And again, the negative just means it's exothermic. Okay, so it's no different. You always want to convert whatever you start with into moles. Always. All right, so let's look at the next one. So this is gasoline. C8H18 is octane, and you're reacting with oxygen, producing carbon dioxide, and water produces an awful lot of energy. That negative got stuck over there. It really belongs here. So I have 17.5 liters of oxygen at 25 degrees and 1.5 atmospheres. Immediately, I look at that and I go, oh yeah, gases. That means it's a gas law. So N equals PV over RT for my gas, which is 1.5 times 17.5 over R and 298 tells me the moles of moles of oxygen are 1.07 moles of oxygen. And once I have it into moles, I'm going to change from oxygen into 1 mole of reaction. 1 mole of reaction is negative 3940 kilojoules. And you get negative 169 kilojoules. So again, the key is always turn it into moles, and then after that you're off and running doing stoichiometry. It's not that different from what you might be used to. So this one's adding some stuff. It says a sample of 67 grams of C3H6 burned in excess oxygen, and all the heat is transferred to a container of water. And I want to know what mass of water could be raised, in other words, heated from 25 to 90. So first thing I have to do is figure out how much heat that's going to produce. So I'm going to do 67 grams of C3H6. 1 mole is 42 grams. And then I'm going to do the C3H6 on the bottom, just like we've been doing. 1 mole of reaction on top. 1 mole of reaction on the bottom. And then I use the delta H, kilojoules, and you do all that math, and that tells you how much heat it's going to produce, which in this case is negative 1641 kilojoules. That's a lot of heat. Okay, again, that negative means it's exothermic. And it's exothermic from the point of view of the C3H6. What you want to identify is how much of that heat goes into the water. So if it's exothermic for the C3H6, it's going to be endothermic for the water. And I just want to point out, this is in kilojoules, and if I plug it into Q equals mc delta T, because we're talking about changing temperature, what I'm going to get is I'm going to have M as unknown, and I want you to notice the units here. This is in joules over grams degrees C, times a temperature change of 65. So if this is in joules and that's in kilojoules, things are not going to work. You need to make them in the same unit. And I don't even care which one you pick, but you have to pay attention to that. So really, I think it's easiest whenever it's in kilojoules and I'm using this equation, I just always multiply by 1,000. That puts it in joules, M 4.18, 65, do the algebra, 6,040 grams. So now when it comes to doing this in the lab, this is where people usually get thrown off. So trying to calculate the value of enthalpy in the lab, first you need to determine the heat that is transferred during some kind of a process. Okay, so generally speaking, you're going to be using this equation, but you are going to be measuring the surroundings. And they're always going to be talking about the system when it's in the lab. But that's the surroundings, and that's what you're going to measure. You're going to calculate that heat. Because you're going to be using a small amount of reactant, you're going to get a small amount of heat out of it. But enthalpy is heat per mole. So you could take the heat that you generate and divide by the moles of whatever it is you're using, and that's fine. But I think based on my experience with what you guys are doing with molar mass, it might be easier to think of it in terms of stoichiometry. So you start with your moles of reactant just like before. Grams turns to moles, liters times molarity. If it's a gas, liters using Pivnert, turn it into moles. Do your coefficient of the reactant, 1 mole of reaction. And this is what you're trying to calculate. You're trying to calculate that. And this is where you put the heat from the surroundings, is right there. Okay? And so you're solving, just like when we were doing molar mass, you would set it up here and you'd solve for that unknown, and you knew how much grams it was. Well, here you're solving for an unknown delta H, and you know how much the heat is. And I think that might work better for people. So for this problem, glucose is oxidized carbon dioxide and water, and it produces heat. That's why you're warm-blooded. I want you to calculate the enthalpy of combustion given all this information in the data. So I would start the same way we've been doing all along. I would start with that 2.5 grams. First thing I would do is change it into moles. It's 180. And then according to the balanced equation, there is 1 C6H12O6 for 1 mole of reaction. 1 mole of reaction is X kilojoules. And then here we're going to put in 39 kilojoules. But here's where you have to think. It says heat was released. That means the energy convention we're going to use, we're going to put a negative in front of it. You have to remember to do that because the delta H here has to be negative because the process releases energy. So when you do the algebra, you end up with 0.0139x equals negative 39. X ends up being negative 2808 kilojoules per mole of reaction. Okay, so it's similar to what we were just doing, except you're solving for an unknown here, and you have to watch the sign that you're doing. Okay, so when you put sodium hydroxide in water, it actually produces a lot of heat. I've done this before. It's pretty exothermic. So if you take 62 grams of NaOH and you dissolve it in 100 grams of water, what you'll find is that the water temperature really goes up. So to calculate the amount of heat transferred, we're going to do Q. So Q equals the mass, the specific heat, and delta T. Okay, you're going to assume the specific heat is the same as water's, so that's going to be 4.18. The change in temperature is from 20 to 57, that's 37. But here's the thing I want to talk about, is the mass. If you're taking 62 grams of NaOH and you're throwing it into 100 grams of water, they're both going to change temperature by 37 degrees. So they are both going to be included in the mass. When you multiply that out, you get 25054. Keep in mind that's in joules. And it's positive because the temperature went from 20 to 57. And so if you do TF minus TI, it's a positive number. To find the enthalpy of solution, that's a delta H, what you're going to do is start with the 62 grams, because that's the stuff that made it change temperature. Change it into moles. 1 NaOH for 1 reaction. 1 reaction is X kilojoules, and that's what you're solving for, equals. So now here's the thing, you have to think about it. If this is my surroundings, where I made those measurements, they took in heat. Their temperature went up. That means the system is going to have the opposite sign. It's going to be negative 25054 joules or negative 25 kilojoules. Okay, you have to watch out for that. The system and the surroundings are always going to have opposite signs. This is positive, that makes this negative. This is positive because TF minus TI is a positive number. So it took in heat, this gave up the heat. If you do the algebra, X ends up being negative 16.1 kilojoules per mole of reaction. That's probably the hardest thing for people to recognize, is when to put in the signs or what to put in for the signs. Probably the hardest thing. Okay, so this one's going to take a little bit of space to do. So you have 45.3 milliliters of NaOH reacts with 52.5. This is the reaction. It's a 1-to-1. So what we want to do is figure out the limiting reactant first. Since they are solutions, liters times molarity will give you moles. So 0.0. So you're going to take the liters and you're going to multiply by 1 liter, 0.1 moles, 1 NaOH to 1 reaction. Oh, we're just trying to find the limiting reactant. I'm just going to turn it into reaction and stop. If I do the same thing with the HCl, 0.0525 liters, 0.1 moles, 1 liter, 1 reaction, 1 HCl. If I do the math, the NaOH is definitely the limiting reactant. This doesn't even count. It's 1-to-1. It's pretty simple. So that's my limiting reactant. Okay. Next thing, you're going to determine the heat release. So I'm going to erase the HCl because it's not the limiting reactant. So to find the heat exchanged, we're talking about temperature change. Q equals mc delta T. Temperature change is 6.3. The density of the solutions is 1, and the specific heat is water. So to find the mass, all I have to do is take this and add them together. And that will be grams because the density is 1. And the specific heat is 4.18. Realistically speaking, with this dilute of solutions, they are almost entirely water. There's very little actual HCl or NaOH floating around, and the temperature change is 6.3. So when you do the math, you end up finding that the heat involved is 2575 joules, or we'll put it in kilojoules, 2.58 kilojoules. And notice it's positive. The temperature went up. Okay? It took in heat. The surroundings took in heat. So in order to calculate the enthalpy of neutralization, you're going to start with the moles, 0.0453 moles of reaction, because I already have that from my previous limiting reactant part. 1 reaction is X kilojoules equals 2.58. However, if that's my surroundings, this is always talking about the system. The surroundings took in the heat, the system gave it up. Do the algebra, X ends up being negative 500 and, oh, I'm missing a 0. 570 kilojoules. Okay, so that's probably the hardest thing, is to recognize the difference between the system and the surroundings. Whatever the surroundings sign is, the system is the opposite, because that's where the surroundings exchange the heat with.